Imagine a restaurant where a customer is a user program and a waiter is an operating system. Kitchen and equipment are hardware like CPU, disk, printer, etc. A customer cannot go directly into the kitchen and cook food. They must place an order through the waiter. In the same way, a program cannot directly access hardware. It must request the operating system using system calls. Here, what is a system call? A system call is a mechanism by which a user program requests a service from the operating system. It is order placed by customer to the waiter. Why system calls are needed? In a restaurant, customers touching kitchen equipment would cause chaos, so the waiter controls everything. Similarly, in a computer, programs directly accessing hardware would cause crashes, so the operating system controls access using system calls. So there are totally five types of system calls are there. The first one is process control system calls, second one file management system calls, and the third one device management system calls, the fourth one information maintenance system calls, and the fifth one is communication system calls. So let us talk about the first one process control system calls. So here we are inside a Linux terminal. Using the Linux command, we list the files present in the current directory. We can see C source files related to different system calls such as fork, execute, wait, read, and write. Let's see fork system call. Now we compile and run a C program that uses the fork system call. The fork call is used to create a new process. When the fork is executed, the parent process continues execution. A child process is created as a copy of the parent. Both processes run concurrently, which is why we see multiple outputs. Demonstrate the execute system call. Unlike fork, execute does not create a new process. Instead, it replaces the current process image with a new program. After execute is executed, the previous program code is completely replaced. That means fork creates a new process but execute replaces the current process. So, exit is a system call used to terminate a process. When a program finishes its work, it calls exit to tell the operating system that execution is complete. This file will be used to demonstrate file related system calls such as write, read, open, and close. Now we run a program using the write system call. The write call is used to write data from the program into a file. This operation happens at OS kernel level, ensuring secure file handling. So, in order to test the text, we use cat. It is a Linux command. It displays the contents of the file on the terminal. And now read. Read is a system call used to read data from a file. The read system call copies data from a file into a program's memory buffer. Here, the open system call is used to open the file and obtain a file descriptor. After completing file operations, the close system call is used to release system resources. Proper closing of files is important to avoid memory leaks and file corruption. Now, device management system calls. These are used to request, control, and release hardware devices. They ensure that devices like printers and keyboards are used properly without conflicts. Device management system calls include read, write, and IOCTL, which are used to control and access hardware devices. Now, let's see their working by executing them. Here, we are using the Nano editor to write a C program named keyboard.c. This program demonstrates low-level input and output using system calls. The read system call reads input directly from the keyboard, and the write system call displays the same data on the screen. Here, we compile the program using the GCC compiler. When the program is executed, it reads input from the keyboard and displays it on screen using system calls. Next, We create a program to demonstrate file output using write and close system calls. This program demonstrates file handling using system calls. The opening call creates a file, the write call writes data into it, and the close call releases the file resource. We compile the printer program using the GCC. After execution, the output is written into a file instead of the screen. Using the cat command, we verify the contents written into the file. The output confirms that the write system call successfully stored data into the file. Next, IOCTL command. This program demonstrates the IOCTL system call. After compiling and executing the code, the operating system communicates directly with the terminal device to perform control operations, confirming successful terminal control execution. The fourth one, information maintenance system calls. These are used to get or update system and process information. Information maintenance system calls such as time, getBit, and uname are used to get system and process information. Now let's see their working by execution. And the first one, time information, which includes time and ctime system calls. What it does, the time gets the current time from the operating system, and the ctime, this converts the time into human readable format. This program retrieves the current system time maintained by the operating system and displays it in a readable format. And the second one, process information, which is getBit system call. What it does, it returns the unique process ID of the running system. The OS assigns a different PID to every process. This program displays the process ID assigned by the operating system to the currently running process. And the third one, system information, uname. What it retrieves, sys.sysname gives operating system name and sys.node name gives system or machine name. Sys.version gives kernel version details. The uname system call retrieves operating system and kernel information maintained by the OS. And the fifth one, communication system calls. Their purpose is communication between processes. These are used for data exchange between processes. They allow programs to communicate using pipes, messages, or sockets. Communication system calls include pipe, socket, send, and receive for inter-process communication. These programs demonstrate IPC mechanism in Linux using pipes and sockets. Let us see their working by execution. The first one, pipe program. It demonstrates communication between processes using a pipe. It creates a pipe with read and write end with FD of 0 and FD of 1. This writes data into the pipe, reads data from the pipe. This program demonstrates inter-process communication using pipes where data written at the one end and is read from another end. And the next one, socket. This program creates a TCP socket, which is the basic building block of network communication. So, in the program, AFINET is IPv4 addressing, SOCKSTREAM is TCP connection, and 0 is default protocol. And the next one is socket communication. It demonstrates data transfer using sockets. It creates a pair of connected sockets for local communication, sends data through socket, receives data from the socket. The program demonstrates socket based communication by sending and receiving data through connected sockets.